So thank you everybody for joining us today. Welcome to another WR Meadows presentation. My name is Isaac Sorensen. I'm an architectural rep with WR Meadows in the Northeast, based in New York City. Thank you for joining us today for Underslab vapor barriers. Our presenter today is Mr. Patrick Rainey. Patrick is an architectural specialist that services our Northern California and Northern Nevada territory. But before I pass the presentation over to him, let's go over a few things. Everyone will be muted for the duration of the presentation. If you have questions, please type your questions into the Q&A box and double check that you're addressing your questions to all panelists. We will be monitoring the Q&A and we'll be attempting to answer your questions in real time. However, if your question requires a lengthier explanation or is a bit more complex, we may hold on to them until the end of the presentation to answer verbally. We may need time to get in touch with you afterward via email for a longer explanation. So this is an AIA accredited presentation, and everyone will be receiving certificates sent to the email address you provided to us at registration. If you included your AIA number, we will also be submitting these credits directly to the AIA. And lastly, on the screen, you'll see an email address, info@wrmeadows.com. If you'd like a copy of the presentation or you'd like to get in touch with your local WR Meadows rep or have any additional questions for us in the future, please send us an email. We would look forward to that. info@wrmeadows.com, and we'll certainly get whatever you need sent over to you. At this point, I'm going to turn over the presentation to Patrick. Patrick, go ahead.
All right. Thank you, Isaac. I appreciate that. Good morning, everyone, or good afternoon, whichever the case may be. Let's go ahead and get started. As Isaac said, my name is Patrick Rainey, and I am your WR Meadows representative for Northern California and Northern Nevada. And I want to thank all of you for taking the time to be a part of this presentation today. And I hope the information that we're sharing today will be helpful to all of you. So with that, let's get started. So who are we? Well, for those of you who don't know, the Meadows Company started in 1926 in Elgin, Illinois. Our company is family owned and operated to this day. And we are very excited that in just a few short years, we will be reaching our 100th anniversary, which of course we are very excited about. We are now headquartered in Hampshire, Illinois, and we currently have 12 manufacturing facilities and 4 warehouses strategically located around North America. And that includes Blue Ridge Fiberboard, which is a part of the WR Meadows family. Here's a map of our various locations that we have in place to serve you in the US and Canada. But I want to also mention that our products are available worldwide. So wherever you may have a project, we can certainly be of help. We started with one product back in 1926, which was asphalt expansion joint, and we now offer over 300 products to help protect your design structures. From our Division 3 offerings that include expansion joint materials to structural and surface concrete repair materials, epoxies and grouts, to our liquid line that includes curing compounds, curing and sealing compounds, and sealers for decorative concrete, to our Division 7 products, starting with underslab vapor barriers and retarders, to air, water, and vapor barriers for above-grade applications, to our below-grade waterproofing systems. And with the soundproofing and insulation board products from Blue Ridge, we have a full line of products to help in protecting the building envelope. So here's a newer item that we've recently developed. This is our master format product organizer for Division 7, which is on our website and was put together to serve as a quick reference document, really. And as you can see, we have a very complete offering of materials for various applications and needs. So again, as Isaac already mentioned, this is an accredited AIA presentation, and all registered architects will be able to collect a learning point for it. And further to that, just another quick reminder as we get going here, that this presentation will be available on YouTube. And if you would like a copy of it, Again, as Isaac mentioned earlier, just email us at info@wrmeadows.com. And we would also ask that you only use the Q&A section to type in any questions you may have and select all panelists. This is the most efficient way for us to address your questions, either verbally or after the presentation, if we have time remaining, or to follow up with you individually after the fact. So we greatly appreciate your help with that. So our learning objectives today are to identify the types of moisture movement that occur below slab, to look at the effects of uncontrolled moisture movement, to discuss various industry standards and test methods. And a little later in the presentation, we will look at product types and site requirements. And lastly, to discuss best practices regarding design and installation methods and how to ensure that you get what you designed and specified for on your project and that it is installed correctly. So as we move into the science of moisture control and come to realize that just talking about underslab or just talking about the below or above grade systems is no longer adequate, we really are now talking about the building envelope or even further along the entire building enclosure. And we need to understand that these components are not independent of one another. They have to work together, be continuous, be compatible, because the underslab is just one part of the envelope. So moisture is everywhere around us, right? So in beginning to identify how to effectively deal with water intrusion, let's think back to our science classes in elementary school. We are all part of the hydrologic cycle, which is the never-ending cycle of evaporation from open water and condensation to produce clouds, precipitation in the form of rain, snow, sleet, or hail, and the dissipation of rain by runoff back into the open water or through the soil. It flows back into the oceans where it will once more evaporate. And the cycling of water in and out of the atmosphere is a significant aspect of the weather patterns on our planet. There are many aspects to the hydrologic cycle and our built environment as we place our buildings around the earth and this cycle in one way or another. So since our buildings interrupt this natural cycle, we must understand how moisture moves and how to accommodate it. So now let's talk about dealing with liquid moisture. How does liquid moisture get into our structures? Well, the presence of water in its liquid form around a structure can be from numerous sources. And in order to select a system that can control water penetration, it's important to consider all of these sources. These sources include the water table. The depth of this needs to be determined and understood, and it can vary from several feet to hundreds of feet. Understanding where the water table is, if it changes by season, if it's tidal, if maybe your structure is located near the coast. These can all play a major role in what you choose for your waterproofing system. Then we have site drainage. How well does the site drain? Is it clay and holds water against your building, or is it sandy and allows water to move away? Is your structure on top of a hill that allows water to drain easily, or at the bottom of a hill? So now you not only have your own site water to deal with, but potentially other nearby sources of water may be draining towards your structure as well. These are all things to consider when you are choosing your waterproofing system. And another factor to consider is the irrigation system. So we are adding extra water to our site with landscaping, plazas and plants and grass areas. And these areas all require water, and many times in excess amounts. And we need to make sure to address those areas as well. Cracks. Cracks allow liquid moisture to enter our structures. Most of the materials we use are concrete based, and concrete does have a tendency to crack. Water can enter through these cracks, and so it's important to understand that, and that the system needs to be designed to accommodate this cracking. Then we have improper waterproofing details. As the old saying goes, the devil is in the detail, right? And that could not be any truer than when we are dealing with waterproofing. As we've already mentioned, these systems need to be continuous in order to deal with all the penetrations, etc. So having good details in your design will go a long way toward a successful installation. And if the detailing is lacking, water will find its way in. So continuing our discussion of water movement in its three forms, let's take a look now at air movement. Air movement supplies a significant amount of moisture. Moisture-laden air moving through gaps and cracks can create serious issues within the building envelope and within our buildings themselves. Types of air movement include wind effect. Wind blowing against a building will pressure air into the structure. Stack effect, a tall building being heated, air moves up. It would be impossible not to address stack effect. Then we have the mechanical systems. Turning on the HVAC system creates pressure differentials, and air will try to move in and out. Not only are there positive pressures, but also negative pressures in stack effect. When air is moving out of the top of the building, it is being pulled in at the lower levels. Most air movement occurs above grade and is addressed above grade, but we also need to realize that air movement does take place below grade as well. Not in the same sense as above grade. We have a lot of gases in our soil. So water vapor is something we are definitely concerned about, but also other soil gases like radon and methane need to be addressed as well. And like with stack effect, warm air rises, positive pressure at the top, negative pressure at the bottom. That is sucking in these gases from the surrounding soil. So our last category of moisture movement from for our structures is water vapor moving from below slab. Water vapor moving through diffusion is any water vapor moving through a substrate other than air. So this is vapor diffusion. So let's consider the soil. The soil acts like a giant sponge. It is completely saturated at all times with 100% humidity. And so no matter what your structure is being used for, it is probably not at 100% humidity in the interior, again, regardless of its use. So when we have this difference in humidity, we have a difference in vapor pressure. And vapor pressure naturally wants to move from areas of high concentration or high vapor pressure to areas of low concentration or low vapor pressure. So think of a balloon that's been filled with air, right? This represents high vapor pressure, okay? But if we puncture a very small hole in that balloon, all of that vapor pressure naturally wants to move to this area of lower pressure. So we're going to have this endless supply of moisture constantly feeding into our structure 100% of the time. And we know that concrete is not a good vapor barrier on its own, so we need to put some kind of material there to block this constant vapor drive into our structures. So let's take a look at the seasonal vapor pressures and drives that occur around our structures. So looking at this slide, that represents a warm summer day, 90 degrees, 80% relative humidity. Well, this creates a very high vapor pressure on the outside of our structures. And the constants are the pressure inside our buildings, where we maintain temperatures at typically around 70 degrees and 30% relative humidity. So this gives us a certain vapor pressure. And then we need to understand vapor pressure from the subgrade, meaning underground and underneath our buildings, where it's generally accepted that temperatures are 55 degrees and 100% relative humidity. And by the way, this applies across the continental US, as determined many years ago by the US Geological Survey. And underground, the time of year or season really does not seem to make a difference. These numbers remain constant. So we have these vapor pressures constantly exerting pressure on our buildings, and Mother Nature is always going to work to try to even out or balance these pressures into equilibrium. So now let's take a look at the same structure in winter conditions. We can see that conditions have changed on the outside, 35 degrees and 20% relative humidity, and our vapor pressure is much less than we saw during the summer conditions, but the pressure inside the structure is the same, and our pressure below the structure is the same. So we still have those constant drives happening 365 days a year. So what does this mean? How can we kind of define this and understand what is really taking place? First, we need to take a look at the vapor pressure underground, which we learned a minute ago is constant at 55 degrees and 100% relative humidity. And according to our vapor pressure chart you see here, this represents 0.214 pounds per square inch. Now, that's a small number in a small space. We'll come back to that in just a minute. Now, if we look at the conditioned space on the interior at 70 degrees and 30% relative humidity, this represents 0.108 pounds per square inch, or about half the amount. So now if we take that pressure differential of 0.106 psi, which puts us up to 15 pounds per square foot of pressure every day, 365 days a year, from below the ground onto our slab and into our buildings. So where does that put us? Well, if you take a look at this slide, that brings us to a significant amount of water when you break it down. You're looking at 10 gallons per day per 1,000 square feet of building. So a 10,000 square foot structure, you're looking at hundreds of gallons a day. So if we take that up to a 50,000 square foot building, you can do the math and really start to see that a significant amount of water is transferring from below the surface to above the surface. And we have to understand that this creates a problem of more issues than we would normally see. The other thing we need to understand is that the vapor pressure differential can change depending on what we are using the structure for. So if we have a structure with, let's say, a clean room, we might have a different vapor pressure differential than, say, a parking structure. So what do you need to be concerned about in terms of vapor drive? Well, we ideally want to get this water vapor transmission rate, or WVTR, as low as possible, ideally down to 0. But we also know that we have all these materials that we can use. So when we are doing that equation, we will be looking at the vapor retarder, but also know that we have these other materials as well to help cut down on vapor transmission. So in addition to the vapor retarder, we have the concrete, any flooring adhesives and flooring material itself. And if you're up north, we're also going to have insulation to possibly consider as well. So all of these different materials combined are going to help cut down on the amount of water that comes into your structure every day. And it's important to understand how hugely important this is. We probably don't need to spend too much time driving home the message in this slide as it relates to our concrete slab, because fortunately, most people, design professionals, specifiers, contractors, etc., know that there are serious consequences involved when it comes to moisture infiltration. And for those that don't, the lawyers are standing by, right? If you catch my drift. So our first concern always has to be the health, safety, and welfare of our building occupants. And uncontrolled moisture coming into our structure provides the opportunity for mold, which we lovingly refer to as the M word, and also mildew growth. And if this happens, our structure cannot perform as it was intended. We can't have a hospital or a school or an office building that is experiencing mold and mildew growth because, quite frankly, it is just not safe for the occupants at that point. And the same thing with odors and indoor air quality. Health of the occupants is the #1 priority. So we want to make sure that the air quality is the best that we can possibly get. And once we have addressed the health and safety of our occupants, we can then turn our attention to our second, but also very important priority, the very expensive flooring that we've just installed. It's expensive to build buildings, and many of these finishes can be very expensive to replace. So if we have uncontrolled moisture infiltration, there can be flooring adhesive failures, especially with the water-based adhesives that are so prevalent today. Moisture comes up through the slab, comes into contact with the water-based flooring adhesives, and reemulsifies, which then turns it into goop. And that's the actual technical term we use for that, by the way, goop. And as far as the flooring material itself, there can often be distortion or delamination. And so those materials would simply have to be replaced. So why do flooring systems fail? Well, we touched on the water-based adhesives a minute ago. And I know here in Northern California, where I'm located, the land of the VOC, almost all of the flooring adhesives used are now water-based and subject to reemulsification if moisture is trapped under the flooring surface. But that's not the only reason flooring systems fail. There's also a little bit of chemistry involved as well. We have to consider the alkalinity of the concrete under the floor. When concrete is poured, it generally has a pH of about 12.5, sort of toward the alkaline side. And as the moisture starts to leave and the concrete starts to cure, it moves down into a neutral place, generally around 7.5, which is ideal, as we want things to be neutral. We don't want acidity and we don't want alkalinity. And at this point, we're in a pretty good situation. Most flooring adhesives today are designed to withstand a pH of 9 or below, so we're in a good place here. However, if vapor drive begins to come through our concrete and get trapped against the tile or the coating that's on the surface of our concrete, the alkalinity starts to rise again and will often exceed that 9.0 number up into the 12 range. And so now we are in that area where our flooring adhesives are subject to failure. So we need to understand the fact that not only reemulsification, but also alkalinity can contribute to flooring failures. So we're going to switch gears a little bit now and look at the difference between a vapor barrier and a vapor retarder. It's very common to hear these two terms used interchangeably out in the field, on the job site, etc. And at one time, ASTM actually did recognize vapor barrier and vapor retarder as equivalent terms, but this is no longer the case. ASTM now only uses the term vapor retarder, and there are very strict performance characteristics for what types of materials can be considered a vapor retarder, mainly the permeance rating of 0.1 perms or below. And it's important to understand that as we are looking at this, that construction materials are permeable, and our retarders have very low permeance ratings, but none of them, at least those that are used in conjunction with an underslab vapor retarder system, have a 0 perm rating. I'm not even sure what does have a 0 perm rating. Maybe glass, maybe aluminum, I'm not really sure. But try putting a sheet of glass underneath a concrete slab and pour concrete over it. I don't think that's going to end very well. So the point is that it's important to understand that all of these materials have some permeance, and there's going to be some amount of vapor going through the retarder. So in looking at vapor retarder characteristics, it's important to understand that permeance and low permeance are necessary to have a positive installation of a vapor retarder. But there's more to it than that. Permeance is important because we have to stop the vapor, right? But we also have other characteristics we have to consider that will help with or aid in the success or failure of these systems. Puncture resistance is certainly equal to, or in my opinion, maybe even more important than the actual permeance rating. And as an example of this, if you take a look at the photo on the right, you can clearly see, if you follow our red arrow, that there is a puncture in this membrane. And all of the products under the ASTM testing standards will have a low permeance rating. So your success is going to come from the puncture resistance as well as a few other characteristics that we'll talk about in a minute. These materials are subject to foot traffic and other general job site conditions. They take a lot of abuse before they are finally covered, and this can lead to punctures in the membrane, which is not a good thing. And even small holes in the membrane from rebar, nails, etc., can allow a lot of water vapor to come through. So for example, some studies have been done showing that a 1/8 inch diameter hole, say a nail hole puncture through the membrane, in a 1,000 foot area of a membrane can change the permeance rating of that area to a 0.93. And if you remember, the industry standard is 0.1 perms or less. So we're already above the recommended perm rating just because of that single 1/8 inch diameter puncture in our membrane. Now, a 5/8 inch diameter hole brings that perm rating all the way up to a 2.2, which is significantly larger than the 0.1 perm recommendation. So yes, vapor permeance is important, of course, but really take a hard look at the puncture resistance of the membrane you're using. So in this situation, while the membrane is still exposed and still accessible to us, we can see the puncture and repair it before the concrete pour. But realize that these are not maintenance products. It's not something that we can go back and fix after the concrete is poured. You know, we can't exactly lift our building up and move it out of the way to patch a hole in the material. We can do things like that if, say, we don't like the color of the walls. We can just repaint it, right? Or if we don't like the carpet, we can just replace it. But let's say if we have a sharp gravel piece under the membrane, for example, and it doesn't puncture the membrane until the concrete pour. Well, in this case, we don't even know it's there. It's not something we can see and not something we can access to fix. So our membrane needs to be durable for the construction site and durable over the lifetime of the building as well. So these materials need to not be degradable over time. And also consider if your retarder is compatible with the surrounding soil of your job site. Are there things in the soil such as methane or radon, or maybe hydrocarbon leftover VOCs, benzene, toluene, that could degrade our retarder over its life? And also, many of these systems can serve multiple purposes. Is the retarder capable of handling methane or radon, for example, or VOCs? So you need to consider, when you're looking at all of these characteristics, what is it that you need and expect from your vapor retarder system? So jumping to another subject now, industry codes and standards and different types of vapor retarders you might see for different projects. ASTM separates the two different types of materials with their own specific performance ratings, testing styles, and they're completely separate. The first is ASTM E1993, the bituminous vapor retarders. They can be more rigid, they can be more flexible. There are really a variety of different products under this bituminous category. But these will definitely be the more robust systems with significantly lower perm ratings, but to go along with that level of performance, also typically more expensive. The more common material we see in typical slab-on-grade applications is the plastic vapor retarders. So ASTM E1745 refers to these materials. And within this category as well, there are many styles of products, different thicknesses, with 10 mil, 15 mil, 20 mil. 15 mil is probably the most common that I see out there on projects today. We have very high puncture resistant products, the gas retarder products, as we referred to a little earlier. So even with two different categories, with two different testing standards, there is a lot of variety within each of these two categories. So the last one for ASTM, which is 1643, is the standard practice for selection, design, and installation and inspection of vapor retarders. And what this is best practices for making sure that the product you select fits the site, that it's designed correctly, and that it is observed correctly prior to the concrete pour. And in addition, the American Concrete Institute, or ACI, as it's commonly referred to, is also involved in this. ACI 302.1R and ACI 302.2R, Guide for Concrete Floor and Slab Construction, and Guide for Concrete Slabs that Receive Moisture-Sensitive Floors, address vapor retarders and permeants. But it's important for us to understand that ACI creates these documents for placement of the concrete in these situations. And we're looking at a document of 40 to 50 pages that only maybe has a paragraph or two referencing permeants and the vapor retarders. So also important to understand is that these ACI guides are not to be used in contract documents. There's a disclaimer on the front of these guides that simply says these guides are not to be used in contract documents. And as all of you know, your specifications are contract documents, so you don't want to use these in your specifications. So let's take a closer look at the two types of retarder systems as defined by ASTM, starting with E1993, the bituminous membrane water vapor retarders. If it's not bituminous, it doesn't meet ASTM 1993. It's that simple. E1993 also establishes physical characteristics, including permeance and strength testing methods and requirements. And looking at these requirements, they are very stringent. Permeance of 0.002, that is extremely low. Tensile strength requirements that are extremely difficult to meet, and they provide excellent performance. A lot of these bituminous materials can be used in multiple applications in terms of water and vapor. So if you're really concerned about your project, although they are more expensive, as we've already mentioned, you might want to give serious consideration to using ASTM 1993 type products. For the ASTM E1745 type products, the plastic vapor retarders, they also have a list of physical requirements. And they break it down even further into Class A, Class B, and Class C type products. And notice that all three of those have the same permeance rating, so they're all 0.1 perms. If they meet the standard, they will have at least 0.1 perm or below. But notice the difference in these classes are for tensile strength and puncture resistance. And as we've already discussed, punctures are a huge deal. If we have a puncture in our retarder, then the perm rating just skyrockets. So that's how we separate this good, better, best categorization, but by tensile strength and puncture resistance. So here are a couple of photos of the puncture resistance testing. On the left is a long metal column. In the middle, we suspend the material at the bottom of the column. And then on the right, we drop that dart from different heights until the material punctures. And I've heard this test referred to as the dart test. And you'll see in the photo on the right that this is a rounded dart. So this is our ASTM 1709 puncture resistance test. But of course, in real life on a job site, we don't see rounded darts being used very often. And I can't remember ever seeing rebar that was perfectly rounded and smooth like this. So although it is a valid test, it really doesn't reflect the reality of what you encounter on a job site. But it does offer the opportunity to compare materials equally to one another, apples to apples. So that's where the benefit of this test comes into play for all of you who are specifying these materials. So I want to talk a little bit about what is an age-old argument of vapor retarder placement. Specifically, do we put sand above our vapor retarder, or do we pour our slab directly onto the vapor retarder? This has been a long-standing argument. And when I first started with our company many years ago and brought this subject up at in-person lunch and learns, let's just say there were definitely differences of opinion on this. If you look at ASTM E1643 back in 1998, it refers to a subsection that discusses the aggregate protection of a vapor retarder. ACI back in 1996 also addressed this situation, and at that time said that vapor barriers / retarders are required to be placed under a minimum of 4 inches of trimmable, compactable granular fill. Well, views have changed. ACI revised their opinion a few years later and stated that these issues should be decided on a case-by-case basis. And frankly, that discussion continues today. So whatever your specification is, the reality is that on the job site, these arguments continue. And frankly, there are valid arguments on both sides of the issue. So I'm not going to say that one way or the other always applies. ACI currently recommends placing concrete directly on the vapor retarder, and WR Meadows agrees with this position. But again, you can have arguments on both sides. So arguments for a blotter layer include a place for water to escape, for bleed water to exit the freshly placed concrete, which can help to minimize slab curling, which the sand can provide protection for the vapor material from job site damage. Arguments against are that you can still have damage whether there is sand on top of the vapor retarder or not. And you introduce moisture into this blotter layer, which actually creates a reservoir of moisture between the retarder and the slab. And once we start seeing this vapor drive and differences in temperature and pressure and humidity, that moisture is going to come up through the slab and possibly cause the types of damage that we've already talked about. These are all valid arguments, and I've been on a lot of job sites, and when you look at a job site and the vapor retarder has been placed, a lot of times the GC will ask the manufacturer's rep to come out and look at the placement before they proceed with their concrete pour, and manufacturers will do that. We certainly do that on a regular basis. So we'll look at the retarder, and if we find any punctures or fish mouths in the tape, etc., we'll advise the contractor to get those items fixed, and we'll write a letter saying something to the effect of that on this date at this project site, the retarder appears to have been installed per manufacturer's instructions. So at that point, you cover the retarder with sand, and the next trade on the job is, you guessed it, the steel workers carrying 20-foot pieces of heavy rebar. And those folks don't want to be on the job any longer than they need to be. So invariably, one of those pieces of rebar gets dropped on our vapor retarder, and the rebar pushes through the sand and punctures the retarder. So the steel worker immediately throws his hands up, stops the job, gets everyone's attention, and says that he may have damaged our vapor retarder, right? Well, this has never happened ever. And if any of you ever do see this actually happen on one of your job sites, please take a picture and send it to me, would you? Here's what's going to happen. He's going to smooth out that sand over the hole he just created, and he's going to go on his merry way. So we have already talked about what punctures do to our system. But since it's now covered with sand, nobody knows. So the rebar gets placed, the details have been taken care of, and you ask us to come back out at a later date to take another look. So at this point, all we can really say is that the sand looks great because we can't see what has happened underneath the sand to the vapor retarder. So we're going to look at a few installation photos now. Here are a couple of photos of the bituminous materials that have been installed. Some are more flexible. What we see here is a more rigid product. The seams are taped here, but you can use a liquid membrane for the seams as well. You can see that a liquid membrane has been used to seal around the base of those pipe penetrations. So the detailing looks good here. In this photo, it's a little more complicated because of those pipe clusters on the left. In a perfect world, we would prefer to detail each of those pipes individually. But in this case, there's no way to get a hand in there to do that. There's just not enough space. So what we do instead is build a temporary dam around the entire cluster and flood it with a liquid membrane so it seals up all those potential gaps and cracks, and it flows through and around those pipes pretty well. This is known as a pitch pan application, and it gives us a great solution to dealing with these conditions when they do come up. In this last photo, by comparison, would be our ideal situation. We have no penetrations whatsoever, nothing to detail, it's just the membrane. So we really have no difficult issues here to be concerned about. You can see that the metal has been placed, and at this point, we are ready for our slab pour. So let's look at a couple of photos of E1745 installations, the plastic vapor retarder materials. Looking at this photo, you can see that the seams are taped. That's the red lines we see here. Those black lines are running across are just a shadow from above, nothing to do with the material. And in the background, we can see some pipes that have been detailed with our system tape. It looks like mesh has been placed in this case, and basically this is a pretty typical installation. Now we see some things starting to get a little more complex. We see pipes that have been detailed, and again, a pretty typical installation and what we would expect to see on a job site visit. And this next photo shows a site where we are basically ready to pour. The seams are taped, penetrations have been addressed, rebar is up on concrete stands, and it looks like we are ready to go. This would be the perfect time to get your rep out to the job to take a look at this installation, because all the work has been done. And even though it's a little difficult to walk around and navigate that rebar, we can still get a good look at everything, make sure there are no punctures and so forth, and make sure we're ready to proceed to our concrete pour. Okay, so let's look further into our systems and make sure we understand what factors can influence the effectiveness of these systems. So far, we've talked about material selection. We want to pick the product that is right for our job. And not every product is right for every job, right? So whether it's a 1993 bituminous or a 1745 plastic, are we concerned about punctures? Are we soil compatible? And then we have system design. We want a system that works within our project and our location and with whatever other parts we are going to be in contact with. Other key factors to keep in mind are workmanship and quality assurance. This is huge. So regardless of the product that you've selected for your project, you have so far selected the correct material, done a great design, and documented it clearly in your plans. But if your installer does not exhibit excellent workmanship, and if we're not able to observe the installation to make sure it was done correctly, then the material selected and the great design you've done doesn't really matter if it's not installed correctly on the job. So it's important to have confidence that your installer is experienced and has worked with the material before, and that they have a team that will raise their hands and say something if there is a problem or a question. As I think we've already made abundantly clear, it's a whole lot easier to address any issues at this point rather than after our slab has been poured. And how well do they work with their supplier and the manufacturer to make sure that they have someone come out to do a final observation before the slab is poured to clear up any potential issues? So all of these parties really do need to work together to make sure this last critical step is not missed. In terms of selecting the material for your projects, it's actually fairly simple. It's creating a list of site conditions that we're designing for. Is this slab on grade? Is there a below grade component? Will this be an occupied space or a parking garage? Will there be any kind of controlled environment on the interior? Is there a high water table or drainage issues or soil gases? If we can identify all of these site conditions that could be challenges, then really it's fairly simple to connect those site conditions to the product that will address those site conditions. Also, something else to consider is what is going into the structure. Are there sensitive floor coverings? Are we doing an epoxy floor? Or maybe we're not covering the concrete at all. Or if we think about something like a gymnasium floor, like a high school or college gym floor or a hardwood floor, these types of flooring systems are very sensitive to moisture and also very expensive to replace. So we need to look at all of these issues within the floor system as well as the systems around. And then there's compatibility. Can I transition to my other systems? Whether we are at slab on grade or do we need to transition to a waterproofing membrane? We want to make sure that these systems we have chosen for our vapor retarder are compatible with the surrounding systems. So looking now at specification. So you've done all this work in selecting the right product and the right system. How do you ensure that you are actually getting what you want on your building? Well, first thing to do is to identify the material type. Are you using bituminous or plastic? Next, you need to identify the level of performance. What are the performance-based characteristics that you are requiring on this project? Once you have type and level of performance, this will give you the correct range of products that are priced out and bid. So these are the two main things to include in order to get the right product. We don't often see proprietary specs for Underslab. There are usually a basis of design or a list of multiple manufacturers. If possible, instead of doing a basis of design or equal, I would encourage you instead to do your research and to list out the exact product name for each manufacturer that you are approving. The reason why is to make sure that the equivalents that the contractors are submitting are actually equivalent in the areas that you care about. And verify which test was used for these different products to achieve those performance values, and ensure that the products that you were putting into your specification are actually apples to apples, meaning same material type and same level of performance. And unfortunately, excuse me, unfortunately, we too often see situations where within one specification, we will see a 15 mil plastic vapor retarder listed right next to a bituminous vapor retarder. And as we talked about a little earlier, these two types of materials have very different levels of performance, very different price tags, very different details, and other physical characteristics as well. So if these two options are presented to your installer, a 15 mil plastic or a more robust bituminous, then realistically, the only products they are going to consider are the less expensive plastic vapor retarders listed. And maybe that's what you want and what you intended, but very possibly not. So it's important to understand that this is not a true competitive spec, because those products are not true equals. And compatibility with surrounding systems. One of the things we have seen over the years, more and more commonly, is the desire to have single source systems. A manufacturer that can provide all the components for the entire building envelope: underslab, below grade, above grade air barrier systems. And creating these single source systems gives the owner and contractor a level of comfort in knowing that these systems will transition easily. If there's an issue, you only have one person to call to handle something that may have happened. So single source systems are certainly one way of approaching it. But if you're not concerned with single source, then just be sure that your systems will transition well between one another. And most underslabs do transition quite easily, but not always. So in terms of substitutions, the VE, the RFI, it's important to consider all these things in that situation. Not all products are interchangeable. Not every product is best suited for your project. So since you've taken the time to select these systems, just make sure that if you get a request for a change or a VE, that product fits into your project. Because if it doesn't, your value engineered product is going to run out of value very quickly in terms of new transitions, new details, possible delays in work, all of those situations that can come up. So here's a quick review of installations. We've already looked at a few. And this is a very good slide because it really does show the ABCs of a 1745 installation. The photo in the upper left was one of my first projects almost 18 years ago at this point, I think, in Walnut Creek, California, for the local municipal utility district. And you can see that they are rolling out the underslab membrane, overlapping the rolls and taping the seams with the special tape that is a part of the system. But you also see a number of sandbags that are holding the rolls in place while the seams are being taped. Well, we often get strong winds here in the Bay Area, and this was one of those very, very windy days. So if you were wondering if this is some sort of special accessory that we offer, it's not. It's just some good old-fashioned sandbags. And in the center, we see the seams being taped. And this is an example of doing it right. They're doing a great job here. One person is holding that tape taut while the other person is adhering it into the system. This is going to ensure good solid adhesion to the seam, which will help to limit fish mouths, which can be just as big an issue as punctures in allowing extra vapor to penetrate. And here at the bottom right, we're almost ready to go here. The multiple penetration system that you see has been taped around. And this, again, is one of the more difficult details to address and can create many problems. But this detailing looks very good. But this photo, again, does reinforce the point that detailing is key to a successful installation. If you take that detail and then look at a cluster that we looked at in the bottom right hand here, maybe this is the detail you're looking for. While the CAD detail on the upper left is fairly simple, it shows the retarder and the membrane floating around the multiple. Oh, Did I miss it? No, sorry. Okay, sorry, I'm in the right place. So here's a specific detail, sorry about that. This detail addresses penetrations. And the CAD detail on the left is very simple. It's the retarder and some tape. It addresses the penetration, and concrete is then poured on top of it. Well, that's pretty straightforward, but looking at the illustration on the right, we get a much better look at an actual single pipe detail. They're fairly intricate, and there's a bit of work needed to make sure we get that tape into the right position and making sure that it's sealed around that penetration and also sealed to the barrier. So if you take that detail and then look at a cluster that we looked at in the bottom right hand, maybe this is the detail you're looking for. While the CAD detail on the upper left here is fairly simple, it shows the retarder and the membrane flooding around the multiple layers. The three-dimensional isometric detail on the bottom right gives us a better look at how that's done. So we built a dam around the cluster, and we fill that area with a liquid membrane that's going to seal around all those individual pipes. So looking now at a few transition details, again, keeping in mind that this needs to be entire building envelope protection, as we discussed earlier in the presentation. So we're going to be tying into other systems as well. This detail is for an elevator pit connection. We have a vertical waterproofing membrane, and that concrete will be poured first, and then we have our plastic vapor retarder overlapping with a liquid membrane that is creating that perfect seam and providing us with continuous protection from the vertical to the horizontal. And here we have a little different situation. We have the slab turning up to additional waterproofing, so we have the vapor retarder underneath, and it will turn up the edge of the slab. The red line in the lower right is just an additional detail membrane offering extra protection on the inside and outside corners there. And then the waterproofing that goes vertical. In the upper left, there's a little round circle at the bottom of the waterproofing that laps on top. And that's just to create another better seal at all of those transitions. So here's a situation that we're asked about fairly often. Do we or do we not wrap the footings? Well, from a moisture mitigation perspective, we would prefer to wrap the footings, again, from the standpoint of moisture control. And unfortunately, this does not always happen because moisture control is not the only thing we need to consider when building a structure. But ultimately, that is the call of the structural engineer or whoever's making that decision. Some do not want to wrap footings because they want the footing in direct contact with the earth and don't want a piece of plastic between the footing and the soil. So we really see this go both ways. So we've covered quite a bit today, how moisture moves into our structures, about the constant vapor drive that exists and why we need to protect our structures against it. We discussed some of the ASTM standards, separating those two different types of vapor materials. Very important in understanding which one you need for your project, and also specifying and designing and installing it correctly. And last but not least, we really want to reiterate that details are critical. Other than the puncture resistance aspect, details are probably the most important part of having a successful system. And again, as the saying goes, the devil is in the detail, right? So getting those details right and installing it correctly are really the key to success where these underslab vapor retarders are concerned. So this concludes the AIA portion of the presentation. Thank you all so much for your attendance. I greatly appreciate each of you taking the time out of your day to be with us for this presentation, and we would love to be your resource for all of your building envelope needs. In this slide, you can see we have several different ways you can contact us or to source the information that you need. The toll-free 800 number you see on the screen is good in all of North America, the States and Canada. And that one number will connect you to the closest WR Meadows location to you. And other ways of getting in touch with us are listed here as well. And of course, our website. We have lots of information available, as you can see here. And we constantly get compliments that our website is very user-friendly. So we've tried to make it as easy as possible for you to contact us or to get the information you need. So with that, I think maybe we have a little bit of a time to look at any questions. So Isaac, I'll turn it back over to you.
Thank you so much, Patrick. Excellent job. Great presentation. Thank you, everybody, for attending. We have a couple minutes now to answer some questions. If you do have them, please put them into the Q&A, and we'll attempt to answer them here for a few minutes. If your question does not get answered, we will certainly get in touch with you soon via email, and look forward to communicating with you there. First of all, we did receive a couple questions regarding how to obtain the presentation. The simplest way to get a copy of the presentation would be to shoot us an email, info@wrmeadows.com, and the presentation will be available on YouTube as well. So info@wrmeadows.com. So we have a few panelists here as well. They may jump in to answer some of these questions, and I'll just go for it. I'm going to ask a few. I'm going to take a second just to get into the Q&A here. What is the name of the liquid product used to seal around multiple penetrations? Patrick.
Typically, what we would typically use around those pipe clusters, I think, is what the question sounds like it's referring to, Isaac.
Yes, yeah, I believe it was your pitch pan there, and
okay, right.
I get
Our product name for that would be Melroll LM, and that information would be on our website too, in that particular data sheet on our website, and in the details. Yeah, that seems to work very, very well. Melroll LM.
So Paul, if you're still here, thank you for the question. If you do need local rep information, do reach out to us at info@wrmeadows.com. We'll get you connected with your local rep to connect you with the distribution point for Melroll LM. Let's see here.
Yeah, and Isaac, further to that, let me just, maybe I should clarify, because we use our nomenclature all the time, obviously. LM, for the person who asked that question, simply means liquid membrane.
Thank you. Thank you for
just to clarify.
Okay, we've got a few more other questions here. Building Science Corporation believes that punctures in a slab vapor barrier are not a big concern since vapor drive is defined by surface area. Could you clarify this? I think just for myself, I would say that sounds a little dubious, and that punctures in the slab barrier would definitely be of concern because they are essentially allowing moisture to pass, to the extent of which is not known unless we understand the penetration itself.
Yeah, Isaac, I'm not sure where to go with that one, frankly. Maybe that's one we need to look at a little more closely after the fact. I'm kind of in agreement, of course, obviously with what you said. So I'm not really sure how to, unless Russ or Roger or anybody else has any input on that. Maybe that's one to look at or answer after the presentation, possibly.
Certainly. We've got another one here. If a puncture is made by a stone or by rebar, what kind of patch size should be overlaid? How large of a patch should be overlaid to the puncture of a membrane?
Yeah, in terms of punctures and so forth, yeah, typically, we would take a piece of the material, overlap it, 12 inches, I believe, and make sure we terminate it with the tape, for example. So we definitely want it to be a larger size. It's kind of, I kind of look at it like this. The same idea as if you have you get a hole in your bicycle tire, right? When you put a patch over it, you're going to put a larger patch, obviously, than what the size of the puncture is. So we've got that specifically in our, in our details and in our data sheets as well. So that's frankly a pretty simple repair. To simply repair a puncture that's visible to us that we can see is not a problem as long as it's repaired. And that's kind of the point, we were trying to make throughout the presentation, is as long as we can see upon our inspection or the contractor's inspection or whomever's looking at the vapor barrier or vapor barrier, there I go, vapor retarder, it's not a difficult repair to make. It just needs to be done.
Agreed. And to second that, Patrick, depending to the question asker, depending on the vapor retarder that's been installed, whether it's bituminous or whether it's a plastic sheet good, should always be per manufacturer's instructions. Those varying different types of membranes have a different approach to, of course, sealing a penetration or a defect that has been made by work being done over the retarder itself. So always refer back to manufacturer's instructions.
Right, and further to that, Isaac, let me reframe what I said a second ago. Actually, if it's just a simple puncture, we would want a piece of the material to overlap in all directions a minimum of 6 inches. And then be taped with the system tape. So a minimum of 6 inches in all directions around the area of a puncture.
We, I think, are out of time here at the top of the hour. Just want to appreciate all of you that were able to join us today, and all those that stayed here for the Q&A portion, although it was rather short. We'll make sure that we get your questions all answered via email, and we'll follow up certainly with everything that was asked today. Again, thank you so much, Patrick, for the presentation. Excellent job.
Thank you.
We'll reach out to everyone, as I mentioned, via email that had asked a question, and to be respectful of the time block that all participants were able to attend, I'm going to now end the presentation. Thank you all so much for your time and attention. We look forward to serving all of your building product needs, and look forward to you visiting our website for further information and for the many resources that we offer here at WR Meadows. So thank you so much for your time and attention. Have a great day, and we're going to end the presentation now.